So I hope you can see it. I'm now sharing the first slide of the raster data in the GeoDBMS. If not, please shout. I hear nothing, so I assume it's going well. So let's have a look at the lecture this afternoon. So why would you like to store raster data? We did already look at extensions for spatial data, points, lines, polygons, also for topology, networks, linear networks, planar partitions. Martijn showed also varioscale representations, but yeah, we did not have a look at raster data or image data in the database. So we'll first spend a moment to think, why is this relevant at all? Then we think, okay, what is needed from the database to support well the management of raster data. As an exception, I will have a more detailed look at the Oracle spatial database and their raster support before going into how it is solved by PostgreSQL in the Postgres raster solution. And finally, I will have a look at a specific database for rasters, or in other terms, multi-dimensional arrays. So not per se only 2D, but also 3D or even higher dimensional arrays. And it used to be the master thesis of Hai-Ching Liu. Okay, you could think why raster in a database or an image, they are relatively static, so they don't need many updates, transactions. The structure is relatively simple. It's rows and columns with values, with say image or pixel values. So you could say there's not so much need for all the advanced mechanisms in the database, transaction mechanisms and multi-user support. It's also true that rasters are taking quite a lot of space to store, and in a database with some overhead even a bit larger. So that's even a drawback. And yeah, the support was very limited and also not yet standardized, and it's still not standardized. So the solution I show of Oracle is different than the solution of PostgreSQL. But there are also good reasons why you should decide to store your raster data in the database. It belongs there with all the other data, with the vector data, with the alphanumeric data. And you can then, when you have all the data together in one environment, you can do also combination queries. For example, you have a polygon of a road, and with a join, a spatial join, then you can select the image from the raster data showing the road from above. Or if the raster represents something else like elevation, you could do, say, an elevation analysis. Having a uniform storage is also easier for the different clients, the applications. They have one way to access the data using SQL. And yeah, the database offer the standard benefits like integrity, also authorization. Are you allowed to use that data? Makes it's scalable for more data, more users, takes care of backups and recovery. So this is all very nice and all very good reasons. And then we wondered what about the performance of having the raster image data in the database, because there is yeah, quite a bit of overhead. And I will show you a little test we did, and you will also do some testing in the lab tomorrow. But there are more reasons why the raster data should be in the database. We have also spatial functionalities that helps with efficient access. So we have the indexing and clustering techniques. And you could say the raster data itself is simple. It has not so much references. The metadata, who collected the image, what device was used, what was the date, could have or typically does have a quite rich structure with references to other tables like persons collecting the image or devices being used, timestamps. So all kinds of attributes and references. And it's also nice to do the raster data operations close to the data where it's managed and that's in the database. And we also have talked to many organizations in practice, and in general, they do have an issue when they do not store the raster data in a database. They said, okay, we have all file-based solutions, but somehow after a couple of years, these files tend to get lost or at least separated from their metadata. So it's less clear what is the date or what device was used, what is the quality of the imagery. So now we came to the conclusion raster data should also be managed by a database. What do we expect from the database? And what are the options? And yeah, we would like to have native support for storing raster data data types, like we have polygon data type or line data types. And you see that there is still quite a bit of development going on. So the PostGIS raster solution is available, but still being worked on and extended. There is a certain vision behind it, and they are still implementing more and more parts of this vision. Oracle calls it GeoRaster, and that's in production, so it's being used and sold. And yeah, the special case of SciDB, the scientific database, if you take a multi-dimensional array and say, okay, we use it as a 2D array, then you could say a 2D array is a raster. And you could also have support for multiple bands, like different colors in the spectrum from satellite images, each having their own raster, their own grid. So what functionality? The data types, georeferencing, of course, the location. Yeah, raster data can be quite voluminous and detailed. And if you then zoom out, you want to have an overview. So that has to do with a kind of a data pyramid, where the higher you go, the more coarser the image gets, but that is fine for an overview on your screen. We would like to have operations, say update operations or image processing operations or other types of operations, and APIs to develop applications against the database. And you would like to be able to input and output the raster data. So that's the functionality side. Performance-wise, it's all about the term called blocking or tiling or chunking to manage the image data and to have fast access and to have overview. So the blocking or the tiling is a kind of spatial organization that can be then indexed with an R tree or a quadtree. Important is the option to be able to compress. Uncompressed data takes much more space than compressed data. And performance-wise, when your data loading, this conversion into the blocks is taking space, taking place and the indexing is taking place. Uh, so data loading takes time. After that, you can do the indexing. That takes time. And then you would like to have, say, efficient data retrieval. So queries should go fast. It could be simple rectangles, but also polygons or other shapes. Okay, here you see the example of a raster data pyramid. At the bottom, you have the highest level of detail, and then you go to higher levels in the pyramid. And then typically, say, 4 cells are being aggregated to 1 cell and get, for example, the average color, or if it's the height, say the maximum height or the average height. And you repeat that until you are at a certain top level, which you are happy with. And it's good to remember that both the bottom level of the pyramid can be tiled or chunked, but you could also still do that for the levels above. So the level 1, as it's called here, and also level 2, because they could still be quite large, and also still indexing could be useful. It's good to realize that in the raster data world, people have a way to put the coordinate reference system a kind of, say, upside down. And normally we have the x-axis on the horizontal, the y vertical going up. But in the raster world, people are often talking about rows and columns. And the columns go from left to right horizontal, but the rows go not from bottom to top, but from top to bottom. They go down. So sometimes in coordinate transformations, you see the map being upside down, and that typically has to do with the confusion of the raster coordinates. Another little confusion is, are you addressing the corners of a cell or the centers of a cell? It does not really matter, but it's important that you document this well in the metadata so that the user can properly use the data, and also the number of values will be different. So if you are thinking center-based and you would have a same size grid, then you would have one value less in the row than if you would have this corner point based interpretation of a raster. Okay, now let's move to an actual available solution. In the Oracle Spatial Database, it looks quite complicated, but it's important to remember these chunks, tiles. Oracle has distributed the solution over 3 tables. In the normal table called the GeoRaster table, they have a column where you can store GeoRaster objects, like you could also have a column to store points or lines. But a GeoRaster object is a little bit of metadata and then a reference to a raster data table. And the raster data table is, say, the collection of the tiles with their extent. And then the cell values are typically efficiently stored, often compressed in so-called binary large objects, blobs. Okay, this is the overview, different tables. So the first table, the GeoRaster table, has a type, data type, where you indicate what is the type of raster. Is it a two-dimensional raster or is it a one-dimensional raster? The number of layers or bands. Is it one value, maybe the height, or is it three bands, RGB? Then you would have three values in each raster cell. Then the time. Is it a time series or is it a single moment in time? And then there's an indicator GeoRaster type, which is more for Oracle internal, does not have so much meaning. So this raster type is the first attribute. Then there is a geometry that gives the complete extent of the raster object. Then there is the reference to the data table. That's the second table. So you store the name of the table in the third attribute. It has an identifier. And in the fifth attribute, you store XML organized metadata. Like, okay, who collected the image, what was the device being used, etc. Then this second table where the chunks are being stored, or tiles. And you can see that also Oracle has this raster pyramid thinking. The object which is used in the second table has the same raster ID, so you know which tile belongs to, or to, yeah, which raster. Then you have the pyramid level. On what level are you in the pyramid? The bottom level or the one above or the top level. Then you have the bands, RGB or other bands, could be bands and multispectral images. And then you indicate the row and the column of the block. And then each block has a little bounding box, a minimal bounding rectangle, which has its own geometry. And then the actual values, say the grid cell values, is stored in the third table with the blobs. Okay, sounds maybe complicated. Also how to use it and how to create it. Luckily, there are some tools that help you if you load an initial image, that there is a function called generate pyramid where you specify the number of levels you want and also how the values are propagated upwards in the pyramid. In this case, it's bilinear resampling to create the pyramid. As said, it's in production, it's mature, it's stable, it's being supported, it's being used in practice quite a lot. There's also quite a bit of functionality, first and all for storing and processing, like creating the pyramid and then retrieving. There is a little bit of image processing functions, not that much, but it's nice that it does support map algebra. And I think you may remember that from your course from Giorgio in the first quarter, Introduction to GIS Cartography, where map algebra was explained. It has limited integration with vector data, so the spatial join idea is not so easy, or a conversion from a raster. Assume you have a raster image, you see on that image a road and you want to convert that to a polygon. That is not trivial. And the multidimensional support is limited. It does support 3D rasters and time, so you could even say 4D rasters at most. But it is possible in the structure to specify it, but the implementation support is not yet there. So you are limited in simple 2D with bands, so image bands and specifications. Okay, dit was de reminder voor map algebra bij Roger Tomlin, where you could have, say, expressions like raster C1 is input raster A plus 10. Then you just add the value 10. So this is local operation. Or you could have two input rasters and say raster C2 is the sum of A and B. Or say other expressions. This is some testing that we did already some time ago. This is an image of Rotterdam, the city center and the river. This data set was stored in 12 GeoTIFF images with 24 bits RGB values with this resolution of 600 million pixels. And the original TIFF files were 1.8 gigabyte. Stored in Oracle GeoRaster, it became a bit bigger, 2 gigabytes, not that much. But with the compression, we could kind of halve the storage in the Oracle database. When then creating 5 levels of the pyramid, the size became bigger again, say 1.5 gigabyte, still less than the original image. And the reason is that TIFF is quite voluminous format because it does not do any compression. So it would be more difficult to beat a JPEG or a PNG image. But okay, it's not too bad, the overhead compared to, say, the native GeoTIFF format. An example of querying. So typically we first figure out which tiles do we need based on the minimal bounding rectangle of the query geometry, and then retrieve these tiles. And then these tiles are being processed to make sure that only the pixels inside the query geometry will be retrieved. And we can query with a polygon or a rectangle or a point. And when we say, okay, we want to have, say, all the pixels in the road, then we have to remove the pixels outside the road. Or in this case, we showed it with an example. Here we see also an effect of the tile size. That's something we can specify when we are loading the data. If the tile size is big, like on the right-hand side, and we were lucky because our circle is completely inside this one tile. We only have to fetch one tile, but it has many pixels that we don't want. So when we make the tiles smaller, we need to fetch more tiles. But in total, the number of unwanted pixels is getting less. But at a certain moment, when you make your tiles too small, they become pixels again, and there is no benefit of having tiles, of grouping the pixels together and index them and fetch them in a fast way. You're also paying. This red polygon is also one of our query geometries next to the circle. It was put somewhere in the middle here of this image. This is the way, I'll make my mouse a pointer. This geometry is the Oracle way of specifying a polygon with the 4 coordinates. And the last one is repeated, as you can see. So we see 5 coordinates. We specify the coordinate reference system. So this will become our query geometry. Then we select from our raster table the right tiles. And with the get raster subset function from our tile, we are getting only the relevant pixels and removing the other ones. Okay, that was Oracle. Yeah, one of the first raster support solutions. The next one I will discuss is Postgres and the PostGIS raster. It is dependent on a number of libraries. One for coordinate transformation, PROI4, and in this case, it is using a lot the GDAL library, Geospatial Data Extraction Library, which has a lot of raster functionality. So the PostGIS developers did not develop everything themselves. They were using this library and making an SQL kind of flavor or interface of the functionality. And if you read the documentation of Postgres raster, they state they want to have a kind of minimalistic but complete raster data structure that is adopting a single type and a single table relational schema. They want it to be very similar to the vector data types. And they say we want it to be very different from the Oracle spatial GeoRaster and raster types, the three table solution. And okay, I will now explain how it looks in PostGIS, and you can then assess yourself if it's very different or not. So they say, again, it's one type, PG raster, instead of two types in Oracle Spatial, the GeoRaster and the SGeoRaster and the three tables. No metadata, no masks, no multiple dimensions, only two dimensions, and bands. So you have two-dimensional rasters and bands, so for RGB, for example. And there's no native of direct support, but the pyramids can also be stored as new images. So in one table, you try to store one raster coverage, and that can be a collection of images, and where the total is possibly non-rectangular. Maybe you want to cover a country or a city, and then yeah, not the cities are not rectangular. And in this table, one row is actually one tile or a raster object. You could say PostGIS raster, PG raster, is actually a single tile. So the table is then a collection of tiles. And together, this collection of tiles covers a big area, but can also make the data pyramid. So the only one raster type, which is the tile or block. It does have some metadata. It does know about the number of rows and columns in the block, things like that. So no metadata in the beginning was a bit harsh. There is limited metadata. There is quite a good level of integration of vector raster functionality. A lot of operations that you see on vector data can also be applied to raster data. And there's also conversion. Maybe this is the easy way from vector to raster. So if you have vector data and you said, okay, I want to work with this as a raster image, then the database offers you a function for that. There are two options to store the raster, inside the database or outside the database. Outside the database has the benefit of having less to load. And you still have then the standard database functionality, the SQL functionality, and all the functions that PostGIS Raster has is available. But yeah, not all the functionality. There's a limited amount of functionality that you have available. Basically, loading and selecting, and not the more fancy operations. PostGIS is working seamlessly on raster and vector data. At least that's the plan. So a lot of functionality that is available for vector is also available for raster. And they have conversions, vector to raster, raster to vector, limited. All the functions that there were for vector data are for raster data, but also the raster data unique functions, they try to make them available for vector data. So kind of integrate, harmonize both types of representations. And here you see some examples of what could be in a single PostGIS raster table. You could have, say, 4 images that were not tiled. So each image is one big tile, you could say. These 4 images are overlapping, partly. Could also be images that are tiled. And in this case, it's even in the example B, it's irregularly tiled because on the right-hand side and at the bottom of a image, you see smaller tiles. So there's a mix of tile sizes. So that's also what PostGIS can do. Okay, option C is probably the more normal one, or C or D, where the image and the tiles are kind of more regular and not of different sizes, more uniform. You can also decide to make multiple tables with raster data, of course. You can make as many tables as you want. That's no problem. And you can also have a lot of empty space in between. The database will store any tile, any image that you want. No metadata. This is the attributes of the PostGIS raster data type, where you see the width and the height of the raster, and things about location and orientation of the raster, and also about the bands and the number of bands. Of course, you need this kind of metadata to work in a proper manner with the raster images. Okay, here are some examples of functions. You can get values and you can set values of the raster cells. You can change the height and the width of a tile or the reference system. So that is the ST. And the counterpart is, ST means it's standardized. And then in one of the parameters of the function, you say if you set or get the value. There are also functions for raster band properties. You can change the pixel values, and not only the metadata, but also the values themselves. You can compute, for example, if it would mean cell values, height, or terrain elevation, you can say also ask for slopes. Query the slope, what is the angle. You can manipulate, make empty rasters with one band or add a new band. And then there are these hybrid functions that combine raster and vector operations. For example, an intersection of a raster image and a vector object. Or convert an image, raster image object to a polygon or to a convex hull, etc. All kinds of conversions, resampling, rescaling, clipping, and conversion to output formats, different output formats. The APIs, okay, available for all the normal programming or mostly used programming languages, Python, C, Java. There are good tools, mainly the ones that are already there in GDAL. And we see quite good support of the Postgres raster functionality. You can use it. You can now access it also in QGIS or in other tools, FME, and also GDAL itself. Okay, you have an empty database, you have PostGIS, you have PostGIS raster support. And what can you do? What can you query? First, you check what version of raster functionality you have available, which version of PostGIS raster is there. You can do that with this query. The second query is an example how to create a table that has a raster attribute. And remember, a raster is actually a tile in a raster most of the time. And you can insert some data, insert into this table we just created, raster number 1, and then somehow encoded the value of the raster cells. And we even insert a second raster, so now 2 rasters are inserted. And then we can do querying. What is the width and the height and the number of bands of these 2 rasters? Typing raster values in the query is not what you want. Typically, the camera has produced some kind of format, image format like TIFF, and you can load that directly into the database. It's good to know what is the content of such a raster file, and you can use GDAL to get some metadata of the whole image with the function GDAL info, then the image. And when you have an image and you want to load it, you have, as I said, we had 12 images to cover that part of Rotterdam. We use the function raster to PGSQL. So PGSQL is the command line interface that creates this insert statement of images. There are a number of flags. The first one is the coordinate reference system. This is the Dutch coordinate reference system 28992. The tile size. And there is a difference between a database where you copy data into a table or where you do an insert. An insert implies a kind of a transaction with transaction overhead. So we said, okay, do not do that. Use direct copy, which is a bit unsafe if there is some kind of crash halfway, but typically much faster. And create an index. That's the I. Then we specify the input files, and we have a wildcard for all the TIFF files in this directory. We specify the table where we want to store it. And then we get a file with SQL statements that create a table, that load the table, that make the tiles. And then to load the actual data, we are running the PLSQL command line interface, and we give this temporary file with the output from the conversion to the database as user Postgres and load it in the database called test. So it's a two-step procedure, loading, bit clumsy, you could say. And we need a lot of temporary storage because the image is kind of converted into SQL statements. That takes storage space for a while. So this can be faster. Like in many operating systems, we can combine the processes, and then the output of one process can be the input of another process. And this is on the command line typically indicated with on the operating system command line, typically indicated with a bar symbol, say a vertical bar. And here you see the same statements, raster to PGSQL and all the parameters and input files, and then the bar, and then the second statement. But this now runs together, and there is no temporary storage of the converted SQL that is directly processed in PSQL and resulting in tables with raster data. And so the second one is more efficient, no temporary storage, but also because of parallel processing. These different processes can run on different cores in your computer and then go faster. They are not sequenced. You don't have to wait for it. Disadvantages of Postgres raster. Okay, you have to make the tiling yourself, but actually the conversion tool raster to PGSQL can do the tiling for you, so with the help of payroll, so it's not a big burden, but yeah, you have to be aware when you are then using the table with all the raster tiles and the pyramids. And there is also not good support for kind of alternative raster grids like oblique images, as you see here on the left-hand side, but also like in hydrography, there are used grids that are following the river shape and not per se rectangular grids. So this is not supported, but okay, maybe you could say it's also quite exotic, not that strange. That's it that you need to know for the assignment tomorrow. Quickly before the break, 5 minutes to a third database called SciDB, which is specialized for, say, multi-dimensional arrays, where the array is not only 2D, like a raster, but can be 3D, like a volume with grid cells, 3D grid cells, or even a 4D or a 5D or a 6D. Raster data can be nice. This is a master thesis example of Michiel de Jong, who made a 3D grid model of a building with walls and floors and ceilings to simulate an evacuation in case of fire. And then there were different users that had to be evacuated from this building. At a certain moment, there are stairs at a number of different locations. At this left side of the building, there is the main stair, but also on the right-hand side, there are some smaller stairs. And here you see in semi-transparent mode the building. You see here on the left-hand side the fire at the start. So the fire is also growing. And you see through this building going like spaghetti, the steps that the user is taking to get out of the building. And we see here a number of different individuals. And as you can imagine, if there are many people in the building, you could get, say, occlusion. But okay, this solution is based on a raster data structure, but not 2D, but a 3D raster data structure. For the community earth science, which is meteorology, oceanography, atmosphere, they have a format called netcdf, which is a kind of the TIFF format for our normal two-dimensional images. They have it, say, in 3D or 3D plus time. For example, if you represent an ocean with grid cells or voxels over time, and that would be a 4D array. And this netcdf is a solution made for that. And netcdf stands for Network Common Data Form. And it's kind of like OGC format. It is also supported now by OGC. There are multiple versions, but it started, say, more than 10 years ago, where a company, Hydrologic, contacted us, say, okay, the performance of netcdf is not good in our weather prediction software. And you have to understand what was the problem. So here is a multidimensional array, a 3D array with latitude, longitude, and time steps, different days of the year. That was stored layer by layer, and a layer is one moment in time, say 1 day. And then within a layer, the cells are oriented in a certain way, like a space filling curve. But if you then do a query for a certain location, let's say you want to know on one location what will be the weather the next couple of days, you have to visit all these, say, purple cells here, here, here. And if you store all the grids next to each other, because the computer memory is basically a one-dimensional array, you have to make big jumps, which makes data access slow. So this time needle query was really slow. And here you see some more options of the dimensions. And what Haicheng did was comparing old netcdf, the new version of netcdf, which is still the current version, and also the SciDB solution. And he had data sets in 2D, 3D, and 5D. 5D means 3D atmosphere plus time plus model run, because they do multiple simulations with different settings. Then you get this, say, 5D data or even higher dimensional data. So these were the two data sets he used: MPE, multi-sensor perception estimate, rainfall data, and GEFS, global ensemble forecast system. So that was up to 8-dimensional data. And he tested all kinds of things, like different sizes of input data, tile size, compression, and compared, here you see tiling options. So these tiles, in this, say, 16 by 16 by 16 space, have all the same volume. But you can imagine that if you organize your tiles in a different way, that for different queries, they may be slower or faster. So this would be a good organization for the time needle in the middle. But on the left, if you want to make a map at one moment in time, this is a very good storage. And you could say on the right-hand side is maybe the best of both worlds. Bit grouping of time and a bit grouping of space. Here you see the actual data sets. And here are some of his results. The message is, okay, SciDB is an interesting database. So whenever, especially when you have higher dimensional raster or grid data, uh, it also has overhead compared to a file-based solution like NetCDF, but it also has the benefit, like other databases, of having uniform access and user authentication. That's it for now. Time for a break. I will stop sharing my screen for a moment. I suggest we have a 10-minute break. And after the break, I will continue with the second part of today's lecture, which is not about raster data, but which is about a third application. So after city modeling by Georgios and energy modeling by Amin, I will show you a third application of databases and information modeling, land administration or cadastre or land registry. Let's say we start at 14:15 again. So a break of 10 minutes. If you have questions, please raise them, and I can also check the chat. I see that you could see the slides. That was nice, that I was not talking for nothing. See you back in 10 minutes. Have a tea or a coffee or another break. Welcome back. It's nearly 10 to 3, and I hope you had your tea or coffee, a bit of rest, a few minutes. The second part today will be a third application. So after the city modeling by Georgios, or the energy modeling of buildings by Amin, we look now at a different application domain, land administration. It's quite different. You could say city modeling, energy modeling, terrain modeling, or 3D modeling in general is kind of about the physical reality. And land administration is more about, say, legal boundaries. They are also in space. You cannot always see them. They can be 2D, they can be 3D. So today I want to give you an introduction into this domain, land administration, also because this year we decided not to do the elective of land administration. That had to do with the busy schedule of the other teacher, Hendrik Ploeger. So I still decided to give you one of the essential elements as an introduction. So today we'll first have a look at land administration as a application domain. Why is it important for society? Then we look at, say, the different parts of land administration. Sometimes it's called land registry, land registration, more the administrative, legal information, and cadastre, which is typically considered more the spatial information, surveying, mapping. But also very important, I will do a quick recap of the information modeling, UML, that Wilco already did, because that is used a lot in modeling a certain application domain. And in one of the next lectures, I will do part 2, where I will go in a bit more detail into a number of topics, standardization in land administration, then the land administration domain model, which is an ISO standard, and I will pay some attention to 3D cadastre. Now, most countries have a two-dimensional cadastre or land registry, but yeah, the world is typically 3D. There are buildings, there are tunnels with different owners. So we need to have also good solution of the legal spaces. Okay, what is land administration? There are several definitions, but these definitions of the United Nations already of 30 years ago is quite good. It's a process of recording and dissemination information, so collecting information and sharing information about, okay, the ownership, the value, and the use of land and associated resources. So associated resources can be natural resources like water, rivers with fish, or mines with metals or oil. But it can also be buildings or roads or infrastructure, utilities. We would really like to know, okay, who is owning what to organize our society. And it's, here's a little bit another definition. It's really a global challenge. And UN Habitat is, hereby expressing how important it is to use the lands in a wise manner, giving, the growth of the population, more and bigger urban developments, the economy growing, and on the other side also the need for good food, enough food, clean water and energy. And they are all competing for space. They're all competing for land. So how, yeah, and sometimes it results in conflicts, wars, or sometimes there are disasters, natural disasters like floodings, tsunamis, landslides, earthquakes. And then the boundaries are not so clear anymore. So here are the UN Habitat websites. And yeah, here you see a lot of people competing for a bit of space. And you could say land administration has a number of aspects. At the top, there is land ownership. And in many countries that falls under the Ministry of Justice. And it's considered a legal aspect or a legal profession, legal discipline. The lower left corner, we have the focus on the land values. And for example, in the Netherlands, this was the reason why the cadastre was introduced, say 180 years ago, because land value is important to know. Land implies buildings and natural resources. Because it's the basis for taxation, but it's also used by banks to give a mortgage or a hypothèque to be sure that the money they provide will be covered by the property. If somebody does not pay the mortgage back, then they at least have the property. So that all has to do with land values. And then we have land use or land use planning. And both in the urban and in the rural and agricultural domain, this is important. So where on the land value side, we saw typically financial sector, Ministry of Finance. In this corner, we see the Ministry of Planning, Development, the Ministry of Agriculture being involved. So from this, you can see land administration is quite a multidisciplinary domain. But I would say it has its roots in geomatics or in the measuring of the land, the parcels. Here you see another image showing the different pillars of land administration. Land tenure is about the titles, the ownership titles, the mortgages, the easements, for example, a way of right. In the middle red on the left, we have land value. We have the land use, and on the right-hand side, we have land development. And these are all linked. These data sets of these pieces of information via the information infrastructure. And it's supporting sustainable development in a country, in a city, in the region. And okay, because nowadays this is all digital, we can talk about e-government, but there's also not only government, it's also the private sector, the land market, the real estate agents, the banks that are involved. So focus on land tenure. And what is land tenure? It's basically linking the land to the people. Who owns what? Who is the owner of what? Or is it shared ownership? Or is one the owner and is other having a long lease? So it's trying to give security to the owners. And because of the security, you also can get a mortgage. And it is then, if you have this overview in the land administration system, in the cadastre land registry, then you can find the information you need, for example, when you are planning to buy a new property, a piece of land with a building or an apartment. And when the information is well maintained, there are less discussions. Uh, so less issues, less debates, less court cases about fights over land, over space. So it supports taxation, the value. It's also good overview of the land use, the inventory. When the owners are changing because of transactions, this is being properly checked and recorded. And many different ministries or departments in government, not only at national level, also at local level, provincial, municipal level, use this type of information. And it's considered nowadays as one of the base registers in most countries. It's important that the information is authoritative, so no doubt that it's correctly maintained by the people who are in charge. It's accurate, so it's correct. It would be nice if it's assured, so that you can 100% trust it. That's not always the case. It should be clear, so unambiguous and available. So you should have everybody should have access. Everybody that needs the information should have access. There's quite a challenge. About 30% of the land in the world of the countries have a good documentation of the ownership of the land. And 70% is not properly documented. That means you have no good rights. That means if somebody in the government says, okay, I'm selling this to a company, that the company can build a factory over there and say, move out the people. So also these informal settlements, they should be given the rights. They should be properly being registered. And this is also what is the policy of UN Habitat, and they try to implement that in or help countries with setting up also a good registration for these more informal settlements. And the rights are not only, say, very formal rights, they can also be informal rights. And it's also important in that case to register them. And UN Habitat talks about the continuum of land rights from, on the left-hand side, very informal, say, perceived tenure approach, customary rights, so native peoples like indigenous peoples living in the Amazon or the Maori in New Zealand, Aboriginals in Australia, they have rights, but they're not yet documented in, or were not documented in the official registrations. Also, being there, living there, occupying space is a certain right if you can prove it, etc. And on the right-hand side, you have the more formal rights like a lease and freehold. So land administration sounds like maybe only land or the earth's surface, but actually it's everything. It is also like the trees and the water and the minerals, and it's everything below the surface and also above the surface, also the airspace. And it's also about the rules. Can certain people own land or split their land? Can land be sold or not? And who is deciding who can do this? And who is deciding on the value or location of the pieces of land that people can buy? So a lot of policy. And here you see that the policy framework in a country is also kind of context or guideline for land administration. As we saw, it's all also based on the information infrastructure. to connect the different functions and also outside information like physical information, terrain elevation, maybe soil for the value, maybe the buildings, because when there's a building on the piece of land, then it's more value. And in every country is different, these rules and the context and the needs. But the purpose is to have good developments, good sustainable development, both in the economic sense, but also in the social and the environmental sense. I mentioned it before when I said land administration is a kind of the legal side and the spatial side, so land registry and cadastre. Cadastre is typically a collection of parcels, but these parcels are defined by law, namely a piece of land or the largest piece of land with the same rights. And yeah, it also has this fiscal aspect to pay tax on that land. It can also be used for future development and planning. And the legal aspects are typically found in the land registry, the owners, the mortgages, the servitudes. It's about this real world. Here you see all the parcels, the pieces of land with a building, with road. On the left-hand side, you could call it the cadastre. On the right-hand side, the land registry. But remember, it really belongs together because the right of an owner is defining the boundary of a parcel. So this right in this document is connected to one of these parcels, and that is then specifying the spatial extent. In many countries, if you don't specify the vertical dimension, only horizontal, like over here, that means you own also everything down to the center of the earth and up into the sky without limits. So parcels, typically 2D. Some countries already have 3D parcels, volumes, maybe for tunnels, maybe for airspace to have a nice view by a piece of air. So land is not the same as terrain in the sense of a topographic map. It is everything included. And in different countries, the organization can be quite different. Sometimes the cadastre is taken care by the National Mapping Agency. Sometimes it is part of Ministry of Environment. So the organization differs per country. Also, the reasons to set up land administrations differs per country. It could be the fiscal or tax reason. Could be the legal reason about ownership to avoid disputes, to support the land market. Could be multiple functions, so taxation, ownership, but also to support land use or land use planning. Then it's important what is the current use and who is owning it. If we look in the way different countries describe the boundaries of the parcels, there are two main approaches. The first one is the general boundary approach. That means these boundaries typically align with physical features, maybe a wall, maybe the edge of a street, maybe a hedge or a series of trees, or maybe the boundary of a river. So they are very closely related to the topography, to the terrain itself, to the physical world. Most countries, however, use fixed boundaries based on coordinates, on surveyed with surveying techniques. And it doesn't matter where is the wall or where is the tree or where is the river. The surveyed boundary is the legal boundary. And okay, these boundaries should be forming closed loops to a kind of polygon and have a certain area. If you look at the Netherlands, we see that Cadastre and Land Registry are in one organization. But that organization also has topographic mapping, is also responsible for support of the maintenance of our national reference network, is also maintaining the overview of the underground cables and pipelines, which is interesting because they are also kind of legal objects. So this is kind of easy because in many other countries, Cadastre and Land Registry are in different organizations, but they are about the same world, about the same pieces of land. And in many cases, that results then in problems and inconsistencies. You see a map of some time ago where, say, in green, Cadastre, Land Registry, and topographic mapping is in one organization. So in Norway, in the Netherlands, in Czech Republic, and Slovakia, and Romania. But in other countries, the situation is different. For example, Cadastre and topographic mapping are together in Portugal and in Germany and in Sweden, but not the Land Registry. That's in a different organization. In yet other countries, Cadastre and Land Registry is together in the blue countries, but topographic mapping is in another organization. So that is in the UK, in France, Iceland, Hungary, etc. And so every country has a different organization. Somehow having the information together is easier to have consistent information. But every country has its own history, which resulted in different agencies or parts of government. Nowadays, you could say, is it important that everything is an integrated database because we have this information infrastructure and we can connect also remote databases. But then you have to make agreements about how to connect these pieces of information. It is important that the coverage is complete, that all pieces of land or space are being covered, and that there's not any part without rights. And there have been some important international initiatives to agree on how to document cadastral parcels. In Europe, INSPIRE, it's the European Infrastructure for Spatial Information, has many different teams, and one of the teams is cadastral parcels. But remember, this is only the spatial part. This is not about the rights that are being registered. Another organization, ISO, International Standards Organization, has made a more complete information model, which is also including the rights that are attached to these pieces of land and which persons. In some countries, this is open data or partially open data, and in other countries, it's not open data. Yeah, actually, it should, of course, be easy to find and easy to use by the citizens. Otherwise, yeah, there are still these disputes or fights about land and development. Here is a little kind of UML diagram where you see the relationship. We have a parcel, we have a person, they are having an association, and the right between these two is the legal information. So the right could be ownership, the right could be lease, or that you have access rights, or that you have rights to collect the fruits from the field. There are all different types of rights that could be on the same location. That is being documented over here. And you can have the case that one parcel can be owned jointly by two persons. And you can also have the case that one person is owning 5 different parcels, but this is the class diagram. A very simple one. So here you see an image where the different types of rights that should be recorded are illustrated with their spatial location. So air rights, development rights for creating buildings, timber rights for the woods, rights of way, okay, where you are allowed to go, water rights, riparian rights, groundwater rights, agricultural rights, mineral rights, etc. I mentioned most of them, but here you see a little illustration. So you should remember 2 things. Land administration, cadastral information has 2 aspects. Spatial information, the cadastral map and the surveying, the boundaries in 2D or 3D. And the administrative information or legal information. Talked a lot about the rights, but it's also important to register the responsibilities. What are you supposed to do? For example, if you own a monument, then you are also responsible for the maintenance of that monument. Or if on your land there is also a waterway, a river or a canal, then it's your responsibility to make sure that the river can keep on flowing. And there may also be restrictions, things that you are not allowed to do. For example, if there is a road on your land that can be used by others, you are not allowed to stop them. So your ownership is also kind of restricted. We already discussed these rights could be more formal or less formal. And traditionally, of course, they were paper-based, paper registers, but nowadays all countries are moving to databases, to digital environments to store. For both the formal and the informal information. And these 2 parts, the spatial and the legal part, they should be linked via unique identifiers. But that's easier when it's done by the same organization, same ministry, than when it's by multiple organizations, multiple ministries or municipalities. So the maps look typically like this. You see black lines that are the parcel boundaries. You see numbers that are the parcel identifiers. And for reference, also the buildings are being displayed. So that you know, with respect to the location of a building, where is your boundary? Actually, the building itself is topographic information. or in the Netherlands, another base register called the Bach. But it's always shown on, no, not always, in 99% of the cases, the buildings are shown together with the cadastral parcel boundaries. Okay, this is the more administrative data, type of ownership, linking it to a spatial unit identifier and to a party unit identifier and a party UID, that's a person. I will, in one of the next lectures, explain more about this terminology. Maybe spatial unit and party are a bit funny terms, but there's a reason for that. Okay, that was the quick introduction to the land administration and the purpose and the main information elements supporting the process of land administration. UML is important. Wilco has given you this introduction to the Unified Modeling Language for information modeling. And if you now check many ISO standards, including the ISO standard 19152, Land Administration Domain Model, UML is used to explain the information contents. And you should remember all these different ingredients of UML, the class, the attribute, the operation, an association, or a constraint, package, a stereotype. So these are elements from the UML class diagram. Next to UML class diagram, there are other diagrams, for example, use case diagram or sequence diagram. They are not used in information modeling, they are more used in process modeling. But now we focus on information modeling. And here you see an UML model. I will not go into explaining the details. I will do that in one of the next lectures. But you see a number of groups. In green, you see everything related to persons, parties, group parties, and membership and group parties. In blue, you see spatial units or parcels, and they have a certain structure. And there is, on this side, there's the surveying aspect to collect the boundaries. And in the middle, there is the yellow stuff, that is the legal stuff. I'm not sure why my drawing is giving you these funny points. But persons are related to spatial units, parcels. And there are a number of specializations like buildings and networks, utility networks, for example. This is the recap of UML, a class, which is kind of the core element, class name, attributes, attribute types, and multiplicity and their operations. Associations link to different classes. They also indicate the multiplicity, how many entities you can be linked to at the other side. And the association can be named, so you know what the association is documenting. Special type of association is generalization, where you have superclass and subclasses. You can add more detail in the subclasses and who inherit everything from the parent or superclass. Another association with specific meaning is aggregation. So a country is consisting of a number of regions, so that's an aggregation. So the region is belonging to one country, and a country has many regions. So that are the associations. Then for the data types, you can have the simple data types like integers or characters, or real numbers or dates. You can have enumeration data types, or like a Boolean, it's only true and false. Or you can have a code list where you can have a limited list of values that are allowed, but this list is extensible. If for some reason maybe there's a new law, there is a new type of right, then we can extend that in the code list. And you can also define new data types, and that is being done, for example, a fraction with a denominator and a numerator. And the operations on a fraction, an equal test or conversion to a real number, and the constraints. So this is UML modeling. I will not go now in the details of the ISO standards. And actually, there are now multiple ISO standards in the land administration domain. The first one was of 2012 that has been used a lot, implemented in quite a number of countries, but all standards are being revised in ISO. And with that, it has become a multi-part standard. And 5 of the new parts are ready. What these parts are, I will tell you the next time. We have some time now for questions, either on the land administration introduction or on the first part on raster data, how to store it in a database. If there are no questions now, you can also post them later. I really hope that Friday I can be in the BK building and manage the traffic and the snow. Then I wish you good luck tomorrow with your last lab assignment on raster data. And I wish you a very good